Now next theorem is, let XD be a complete metric space if A is totally bounded, then A is relatively compact. So in the previous lecture, we proved that every relatively compact set are totally bounded, but converse is not true. So converse is true only in the complete metric space. Now in the given part, the given is X is complete metric space and A is totally bounded. So our purpose is to show that A is relatively compact. So what is the definition of relatively compact? Every sequence in A closure has a convergent subsequence. Has a convergent subsequence in A closure, right? Because A closure is compact. Now suppose since A is totally bounded, then it means it has finite epsilon net. Suppose epsilon equal to 1 because epsilon is some arbitrary number. So we take epsilon equal to 1. Clear? And this is a epsilon net y1, y2, yn. It is a epsilon net. It means these are the center of sphere which cover A. Clear? These are the center of ball which cover A. Right? So it means A contained in ball with y1 epsilon, y2 epsilon, yn epsilon. Here epsilon is 1, so we take here 1. This is by definition of totally bounded. Let Xn be a sequence in A. Our purpose is to prove that every sequence in A has convergent subsequence. So remember that. So we take Xn be a sequence in A. If Xn is a sequence in A, so this is A. Clear? So Xn belongs to A. A is a part of this. So that sequence belongs to these balls because sequence contains infinite numbers. So infinite element belongs to any one of the ball. Clear? From these ball, we can find a ball B1 such that B1 contains infinitely many points of sequence X, right? That we already discussed. This sequence, it contains infinite elements. So infinite element belongs to A. Some goes to this ball, some goes to this ball, some goes to this ball. So infinite ball maybe go to any one of the ball. That ball is treated as B1. So it means we can find a ball B1 such that B1 contains infinite many points of sequence X. It means B1 intersection this set which contains infinite many points that we written as x1 comma n. 1 is related to ball 1 and n is related to this sequence. So what is this? It is a subsequence of this sequence xn. And what is this? This, it belongs to ball b1, right? So it belongs to ball b1. So where x1n subsequence of sequence xn and it is also member of b1. So it satisfies two conditions. One, it is subsequence of this. Second, it belongs to b1. b1 is ball with the center any one of these and radius is 1. Clear? So this vector, this element belongs to that ball whose radius is 1. Now, similarly, by assumption, A is contained a union of finite many balls of radius 1 by 2. So first we take epsilon equal to 1. Now in second step, we take epsilon equal to 1 by 2. So it means A is contained in finite union of ball whose radius is 1 by 2. Clear? So going to same procedure, by using the same procedure, what we get? We get from these B2 contains infinite many points of sequence xn such that B2 intersection xn which is equal to x2n. Clear? Now again it satisfies two conditions. One, it is subsequence of this sequence. Second, it belongs to ball B2. Now this ball B2 has radius 1 by 2. Remember, B1 ball has radius 1. B2 ball has radius 1 by 2. Clear? Again, now we take epsilon is equal to 1 by 3. And same procedure. Then 1 by 4. Then 1 by 5 and so on. Similarly, continue the process. We can find a open ball BR with radius epsilon equal to 1 by r such that BR intersection xn which is xrn. This xrn is a subsequence of sequence xn, number 1. Number 2, xrn belongs to BR. So what is BR? BR is an open ball with radius 1 by r. Clear? So we get a sequence of subsequence. So we get it is a first sequence. It is a first sequence. It is a second sequence. It is a rth sequence. So what we get a sequences of subsequences. Yeah. So we get sequences of subsequence, which is a subsequence of xn, which follows the following result. Number 1. This is x1, x1 to x13, and this sequence belongs to B1. Clear? This sequence belongs to B2, and this sequence belongs to B3, and this sequence belongs to Bn. B1 is a ball of radius 1. It is a ball of radius 1 by 2. It is a ball of radius 1 by n. It is a ball of radius 1 by n. Right? Now taking diagonal entries x11, x22, x33, xn. Now x11 belongs to ball B1. This belongs to B2. It means its distance is less than 1. Its distance is less than 1 by 2. Its distance is less than 1 by 3. And it's 1 by n. Now this treated as y1, this treated as y2, this treated as y3, this treated as yn. So we get yn, this xn, or this yn belongs to bn. This is a ball with the radius 1 by n. Remember this. So this is a subsequence of xn. Now this distance between yn comma y less than 1 by n for every y belongs to A because it belongs to ball Bn. Now for epsilon, if we choose a positive integer capital N greater than 1 by epsilon, then it satisfies this condition of convergence. So how we can choose this term less than epsilon? Okay? So simple, remember our purpose is 1 by n less than epsilon. Clear? 1 by n less than epsilon means n is greater than 1 by epsilon. Clear? So I repeat this 1 by n, if less than epsilon, then this small n is greater than 1 by epsilon. So we choose that integer which satisfies this condition. It means we can find a positive integer capital N such that which is greater than 1 by epsilon. Here it was small n. Here we choose capital N. So when this small n greater than equal to capital N and capital N is greater than 1 by epsilon, so automatically small n greater than 1 by epsilon. Clear? If small n greater than 1 by epsilon, then 1 by n is less than epsilon. It means this term is less than epsilon under this condition. It means the sequence yn, this sequence yn, is a Cauchy sequence in X. This sequence yn is a Cauchy sequence in X. We know that this is a Cauchy sequence. If it is a Cauchy sequence in X and X is complete, then there exists Y belongs to X such that this yn equal to Y, it belongs to capital X. So this sequence is convergent. So this sequence is convergent and also it converges to the point of X. Clear? So it is convergent and also it is converged to the point X. Now from this, what we conclude? From this, now here this Y belongs to A. Here we know that only this sequence is convergent. If this sequence is convergent, then it is Cauchy. Now our purpose is Y belongs to capital X. If this sequence is convergent and this is a Cauchy and X is complete, then it converges to a point belongs to X. If it belongs to point X, right? Clear? Also we know that yn belongs to A, it implies Y belongs to A closure. It implies Y belongs to A closure. If Y belongs to A closure, then by definition of closure, there exists a sequence Zn in A bar such that distance between Xn and Zn less than 1 by n for every n. Clear? So this is by definition of A closure. So distance between Yn and Zn, this is less than 1 by n. Distance between Zn and Yn. Clear? Now from this, since every sequence Xn in A has a subsequence Yn, right? This is a subsequence of Yn, which converge in A closure, by previous result. Hence, Zn is also subsequence of which converge in A closure. Why? Because this distance between Xn and Zn is less than equal to 1 by n. It implies A closure is compact. If A closure is compact, then it implies A is relatively compact. So it means every total boundedness implies relatively compact, but it is only in the complete metric space. So this is possible only in the complete metric space, right? So this is possible only in the complete metric space. So in the complete metric space, every relatively compact are totally bounded and every totally bounded are relatively compact. So there is no difference between relatively compact and totally bounded only in case of complete metric space. This is very tough theorem and also important. Now next is, let Xd be a metric space. If subset A of X is totally bounded, then for every epsilon greater than 0, it has finite epsilon net such that that set is part of A. Yeah. Here our purpose is the epsilon net always part of A. That's all. Now if A is empty set, then we have nothing to prove. If A is not empty, suppose A is not empty, then by definition, for given epsilon greater than 0, there exists a epsilon net. What is epsilon net? M epsilon 1, which is part of X for A. This is epsilon net for A. Here it is a part of X, not part of A. Our purpose to show that it is a part of A. Clear? So this is a part of X. So this is epsilon net for A, but part of X. Now, if we choose epsilon equal to epsilon 1 is equal to epsilon by 2, then it means A is contained in the union of finite many open ball with radius epsilon 1 with element of M epsilon 1 as a center. Clear? So that is the definition. So suppose these M epsilon 1 contains point x1, x2, xn, then this means A is part of Bx1 epsilon 1 union B of x2 epsilon 2 union B of xn epsilon. Clear? Now, since A is a subset of this and A is non-empty, it means its intersection with this is non-empty. For J is running from for J is running from 1 to up to n because it is non-empty. And if this is a non-empty, then there exists some Zj belongs to this intersection. And it implies this Zj belongs to A and Zj belongs to B of xj comma epsilon 1. Clear? Zj, because it belongs to intersection. It belongs to A, it belongs to B xj comma epsilon. These values. Now consider a set S which contains Z1, Z2, and Zn, or this is a part of A. Why? Because Zj belongs to A. This is a part of A. Clearly. Now, since Zj belongs to this ball, so it satisfies the distance between these two is less than epsilon 1. So this is less than epsilon 1. Clear? So what we get? We get for every Z belongs to A, it implies Z belongs to Bxj epsilon 1 for some J. Why? Because A is a part of these union. If we take Z belongs to A, it belongs to this union. If it belongs to this union, then it belongs to part of any one of them. Then it implies this Z belongs to Bxj epsilon for some J. Why some J? Because it is a union. It belongs to either first ball or second ball or third ball. That's why we use some J. Then by definition, distance between Z and xj less than epsilon 1 for some J. Now, dz z comma zj by triangle inequality. This can be written as z comma xj plus xj comma zj. This term is less than epsilon 1. This term is less than epsilon 1. This is by 4. This is by 5. We check that. This is by 4. And this is by 5 by triangle inequality. It means this difference is less than epsilon. It means this z belongs to this ball where J is running from 1 to n. It means the element of A belongs to first ball or second ball or third ball or nth ball. It means A is part of Bz1 comma epsilon union Bz2 comma epsilon and so on. Also we know that this set is a part of A. Also, we know that Z1, Z2, Zn, these are part of A. And what is this? It is epsilon net. If it is epsilon net, also part of A, then what we get? There exists a finite epsilon net for A such that M epsilon is a part of A. So which proves the result. That is our result.